Okay, so in this video, we will consider our first example of finding the area below a curve over a given interval exactly using the limit of a Riemann sum. So here's the exact curve and interval. So we want to find the area below the quadratic polynomial f of x being 2x squared minus 4x plus 5 over the interval from x being negative 1 to x being positive 2. Well, first let's just produce a rough sketch of the curve just to get a feeling for what we're actually evaluating. Well, we have a quadratic polynomial. The multiple of x squared is positive, so we'll have a parabola facing upward. Just to have a slightly more accurate sketch of this parabola over the interval, we'll find the apex, which is the critical point, right, where the derivative is 0. So if we find f prime of x, and when you sketch a parabola, it's really the only point you need. Look if it's upward or downward, and then find the apex. So the derivative is going to be 4x minus, 4x minus 4. If you factor 4, you get 4 times x minus 1. And this can only be 0 if and only if x is equal to 1. So x equals 1 is the apex of our parabola. Here this would be the global minimum. And the value of our parabola at 1 is, well, 2 minus 4 is negative 2 plus 5 is 3. So now we can very easily create a pretty accurate sketch of this polynomial. Well, the interval goes from x negative 1 to x is positive 2. And on this interval, the apex is at x equals 1, and f of 1 is 3. So at this point right here, the derivative is 0. So the parabola will look something like this. The point where the derivative is 0. So the question is to find the area below this curve between x equals 1 and x equals negative 1 and x equals 2. So this is uppercase A, the area below our curve. Well, we know how to find A. We've derived a way to find A by the limit of a Riemann sum in our previous video. So let's look at it. We'll write out the general formula, and then we'll replace for the given values of A and B, and the function will simplify, then take the limit. So we know the exact area will be given by the limit as n goes to infinity, n being of course a number of rectangles. We have to sum I being the first rectangle, so I equals 1, then 2, then 3, all the way up to the nth rectangle. The area of each rectangle, well, that's easy, right? We need the height of the rectangle, so f of xi, times the width, delta x. And now we have the exact area below our curve. Well, let's compute xi, delta x, and f of xi, then find the sum, then let n approach infinity. Well, what is A? A is the left-hand point of the interval, so A is negative 1. B is the right-hand point of the interval, positive 2. Delta x, the length of the interval over n, but B minus A, 2 minus negative 1 is 2 plus 1, 3, 3 over n. So we have our delta x. Delta x is 3 over n. So we have delta x. Well, to calculate f of xi, you need xi. Well, what is xi? Well, xi, if you remember, is a plus I delta x. So we start with the left-hand point and we add I steps of delta x to obtain the right-hand point of the ith interval. We can now replace a is negative 1 plus I times delta x, but delta x is 3 over n. So I delta x is I times 3 over n, or I'll write 3I over n. So 3 over n times I. I'm just swapping I times delta x for delta x times I. So now we have xi, the right-hand point of the ith rectangle. Well, the next step is to compute f of xi and to simplify. So don't plug this in now to the summation and then simplify the function within the summation within the limit. Take it aside. Evaluate f of xi, simplify. Once it is fully simplified, then we'll plug it back in. So, let's calculate f of xi and simplify. And once we have it simplified, then we'll plug into our summation. Alright, so this is a simple substitution. F of x is 2 times x squared minus 4x plus 5 for any x. Now we are simply replacing x by xi. So f of xi will be 2 times xi squared minus 4 times xi plus 5. And now we can replace xi by this expression and simplify. So 2 times xi squared, but xi is negative 1 plus 3 over ni all squared minus 4 times xi, negative 1 plus 3 over n times I plus 5. Let's expand and regroup similar powers of I. So we'll have 2 times. If we square this, we'll get negative 1 times negative 1, positive 1. Negative 3i over n, negative 3i over n will give you negative 6i over n. Positive 3 over n times I times itself, 9 over n squared, I squared. Negative 4 times this. Here, I'll leave it for like this for now, then we'll multiply out. So minus 4, negative 1, plus 3 over n I, plus 5. Now we'll expand and regroup similar powers of I. So if we multiply, what do we obtain? Well, 2 times 1, 2, minus 2 times 6, 12. 2 times 9, 18. Minus 4 times negative 1 plus 4. Negative 4 times 3, negative 12 over ni, positive 5. And now we'll regroup. There's a single quadratic power of I, so that's 18 over n squared, I squared. The multiples of I, negative 12 over n, negative 12 over n, negative 24 over n times I. And the constant term, 2 plus 4, 6 plus 5, 11. And now we have f of xi fully simplified. 18 over n squared, I squared, minus 24 over ni plus 11. And now we're good to go. We can calculate the area now by replacing our simplified f of xi and our delta x by, of course, 3 over n. So let's do so. And I'll start on a fresh page. I'll rewrite this first and remind you of what is f of xi and delta x being 3 over n. So I'll just recopy these three things first, and then we'll go from there. And you'll see that we're on our way to finding the exact area now. So the exact area is the limit as n goes to infinity, the summation as I goes from the first to the nth rectangle, height of the rectangle, f of xi, times the width of the rectangle, delta x. But now we have found, and I can remind you here, both f of xi and delta x. So the area is the limit as n goes to positive infinity, the sum as I goes from 1 to n, f of xi, let's replace, f of xi times delta x 3 over n. And now all that's left is to simplify this summation and then let n go to infinity. And surprisingly, this may look bad, but as we'll see, things work out very nicely, and from this point on, things are really straightforward. So, we're going to use here properties of sigma notation and our fundamental sums. First property, we are summing this term times this term. But we're summing with respect to I, so I is changing. But if you look here, it's 3 over n. There is no I here, as I is the only variable changing here, as we are summing with respect to I. So I changes from 1, 2, 3 up to n, but n is fixed, n is the number of rectangles. So we can pull the constant term 3 over n outside of the summation. That is the first property of sigma notation. We can move constants in and out of the sum. Here we're moving the constant with respect to I outside of the sum. Now we're going to use our second property of sigma notation to break up the sum of these three terms into three separate sums. If we're summing over a sum or a difference of terms, we can sum the terms individually and then subtract and add up these individual sums. So let's do so. So we'll sum these terms first. Then we'll subtract the sum of these terms. And then we'll add the sum of the last term being 11. Alright, now what? Well, we can go back for each sum and use property 1. As we're summing with respect to I, 18 over n squared is a constant, we can pull it out of the sum. 24 over n is a constant, we can pull it out of the sum. 11 is 11 times 1, we can pull 11 out and be left with a 1. And let's see if you can spot what's interesting about this stage now. Pulling this out. Pulling this out. Pulling 11 again, as I've said, 11 times 1 gives us 11 times the sum, I going from 1 to n of 1. And why is this great? Look at the sums that we're left with. The sum of 1 from 1 to n, the sum of I from 1 to n, the sum of I squared from 1 to n. These are our first three fundamental sums. And we know how to evaluate these sums with the shortcut formulas we have derived in previous videos. This one is very simple. If you add 1 n times, you get simply n. If you add I from 1 to n, this is 1 plus 2 plus 3 plus 4 up to n. Recall this was simply n times n plus 1 over 2. And look at your third fundamental sum. If you add I squared from 1 to n, so 1 squared plus 2 squared plus 3 squared up to n squared, this is equal to n times n plus 1 times 2n plus 1 over 6. So now we can replace each fundamental sum by its shortcut formula. And I will have, in the end, a simple function of n without any summations. After we simplify, we'll be able to let n go to positive infinity and obtain our exact area this way. So we're almost done now. So let's replace. So 18 over n squared times the shortcut formula. So n plus 1, 2n plus 1 over 6 minus 24 over n times n plus 1 over 2 plus 11 times simply n. And you see, no more summations, because we've replaced each fundamental sum by its shortcut formula. And now we can simplify this a little bit and then evaluate the limit. Now here, don't multiply these out. The idea will be to pair up each n with an n on the denominator, and this will simplify the limit greatly. So let's simplify a little bit. The 3 will leave here, and I'll multiply through this by 1 over n. If there's ever a constant multiple up front, leave it there. It won't do anything except at the very end you'll multiply what you have here by 3. So bring the over n inside. But before we do so, let's simplify. We have an n over n here. This cancels. It's just 1. We have an n over n squared. So you can cancel one of the two n's here, as n over n squared is 1 over n. This goes away. That's pretty much it. We can cancel a little bit more, right? That's it for the n's, but now we have the constant terms. 24 over 2, that's just 12. 18 over 6, that's just 3. And now we'll rewrite this, and we'll also bring in the n. So what are we going to have? We'll have 3 n times n, 3n squared, times a leftover of n plus 1 times 2n plus 1. Then what? Minus 12. Bring in the 1 over n, right? Multiply every term by 1 over n. Will leave you with negative 12 n plus 1 divided by n. Plus, this one will be quite simple, 11n over n. And now what's the idea? We're 2 steps away from being done here. And again, I want to emphasize not to multiply these out. If we're clever, we can obtain a very, very simple limit. So 3 There's an n here, there's an n here. What I'll do is I'll split up the n squared as an n times n, put one n here, one n here. So n plus 1 over n times 2n plus 1 over n. So n times n is n squared. Minus 12, n plus 1 over n, plus 11, n over n. And now I will divide each one by n, and we'll have what you'll see, a trivial limit. Well, n plus 1 over n. N over n is 1 plus 1 over n, so it's 1 plus 1 over n, times 2n over n is 2 plus 1 over n minus 12 times n over n is 1 plus 1 over n, so 1 plus 1 over n, plus 11, n over n is 1, so it's just plus 11. And once that's done, you'll see we have a trivial limit now. As n goes to infinity, 1 over n shrinks to 0. As n gets bigger and bigger and bigger, 1 over it will get smaller and smaller and smaller. As n goes to positive infinity, 1 over n will just shrink to 0. And all we have are 1s over n here. And now look at what happens. We've let n go to infinity, so we don't have to write the limit again. What are we left with? 3 times. This is 3. As this term, 1 over n goes to 0, that's a times 1, times 2 plus 0 is 2, so times 2. Then minus 12 times this term, but this 1 goes to 0, so times 1, plus 11. It's a constant. And now we can just evaluate this. 3 times. 3 times 1 times 2 is 6, minus 12, plus 11. But 6 minus, or actually do it this way, negative 12 plus 11 is negative 1, 6 minus 1 is 5, and 3 times 5 is 15. So we catch our breath here and ask or remind ourselves, what's this 15 about? Well, 15 was the area below the curve. Limit of the Riemann sum. Simplify your f of xi, plug in delta x. Properties of summations. Shortcut formulas for the fundamental sums. Simplify the function of n, so then you can evaluate the limit quite easily. And we have the area below our curve to be equal to 15. And you can appreciate that this was not a trivial question. I mean, look at how much work we had to put in to find an exact value for the area of 15 units squared. If you want, we can go back to the picture just to include now the final answer. So if you go back, you see the curve was y equals 2x squared minus 4x plus 5. And if you look at the area below this curve, from negative 1 to 2, the area is exactly 15. And that's it. So with this now, with the help of our 4 fundamental sums, so summing from 1 to I squared to I cubed, you can evaluate the area below any polynomial of degree up to 3. If we wanted to go up to 4, 5, 6, and so forth, we would simply add more of our more fundamental sums to our list, as these kind of formulas exist for summing I to the 4, I to the 5, and so forth. But with what we have right now, we can find the area below any polynomial of degree up to 3 by evaluating, as we have just done, the limit of an appropriate Riemann sum. And that's it.